All right, so let's get started on the caches practice problems. So we'll start out with the review. So first write down your own answers and then you'll discuss them. And so here we have 2 questions. So go ahead, pause the video, answer the questions first on your own, then discuss them with your partner. All right, so how do caches give us the illusion of both a large and a fast memory? Well, we get the fast memory because caches are small, so the memory itself can be pretty quick because it's a small memory. Then we need to figure out how we make it look large. And the way we make it look large is by keeping the right data in it. So we get the right data from our large main memory, keep it in the cache, and then we have something that looks big because we have the right data and it's fast. And the trick is all about how do we keep the right data in the cache. And how do we do that? Well, what we've talked about in this class and what is mostly what people still do is you keep the most recent data. The idea being that if you use the data recently, you're likely to use it again. Okay, why do we need tags in caches? Well, the reason here is because we put data in the cache, but we can put all sorts of data in the cache. So we could put addresses 1, 2, 3, or 10, 11, 12 in the cache, and we need the tags to know what the addresses are. So the tags tell us, is the data we have in the cache from addresses 1, 2, 3, or is it from addresses 10, 11, 12? Because then when we go to look in the cache, we need to know what addresses are in the cache so we can access it. So essentially the tag tells us the address of the data that's in the memory, and we need to have a tag because we can put any addresses in the cache. Okay, let's go ahead and take a look at what goes into and out of a cache. So go ahead, take this design here. You've got a processor memory in your cache and draw what the inputs and outputs are on it. So go ahead, pause the video, answer this together with your partner. Okay, so let's see what we've got here. So from the processor, we've got addresses that come out. This is the data it wants to access. We've got data that goes out if we're writing and data that goes in if we're reading. And on the memory, we have the same thing. We have the address we're going to access, data going out into the memory if we're going to write to the memory, and data coming out of the memory if we're going to read from it. And the cache sits in the middle. So the cache is going to have the same connections on both sides that the memory and the processor have because it sits between them. So let's take a look at how it works here. So inside the cache, we're going to take in an address. We're going to use the address to search the tags, and we're going to see if it's a hit and return the data. So let's say we have a load word instruction that comes in here, and let's say it's a hit in the cache. So what happens? Well, the processor is going to send the address into the cache. The cache is going to look in the right place based on that address, and it's going to compare the tag that comes out of that with the address to see if it's a match. If it's a hit, then it's going to say, all right, we've got the data, and we're going to return the data to the processor. And so this is why caches are faster, because if you find the data in here, you'll return it, you'll get it more quickly. But let's take a look at a load that's a miss in the cache. So here our load goes into the cache, we check it, we compare it to the tag, and we find out it's a miss. So that means the data that's stored here in the cache isn't the data that we were trying to load. So what do? Well, the cache then goes on to the memory, sends the address over the memory, gets the data back from the memory, puts it into the cache so it can use it in the future, and then returns it to the processor. And this now is a little bit slower actually than accessing the memory by itself, because you have to go through the cache first and then the memory. But remember, today the memory takes hundreds of cycles and the cache takes 2 or 3 cycles. So even if you have to do the cache before you go to memory, it's not a big deal. Every time you hit in the cache, however, it's a big savings because it's so much faster. All right, now we're going to test out being a cache. So we're going to run through what a cache actually does ourselves, and we're going to do it in a way that's related to something you may be familiar with, which is a phone book. Actually, you're probably not familiar with phone books because nobody uses them anymore. You just Google everything. But let's take a look at the problem. So you have a phone and you want to display the name. So when a call comes in, you need to get the name based on the number. So you get the number when the call comes in, you have to look up the name. So for example, if you get the number 781-729-5555, you need to return Frank because that's Frank's number. You have some resources here. You have a phone book, which has 10 billion numbers and names in it. So it takes you 10 seconds every time you go to the phone book to look up someone. And you have a bunch of desk drawers. You have 10 drawers, and it takes you 1 second to go into the drawer, 1 second to look inside it, or 1 second to put something in the drawer. Now, each of these desk drawers can hold 1 piece of note paper, only 1 piece of note paper, and there's space for a number and a name on that 1 piece of paper. Okay, so here's the setup. You've got a phone book, takes 10 seconds to look up. You've got 10 desk drawers that take 1 second each to access. Your job is to figure out how to use the phone book and your desk drawers to find your numbers quickly. Okay, this should look somewhat like a cache too. So the first part, a policy. So you need to figure out how are you going to do this? What are you going to do first? What are you going to do second? How are you going to know if you have the right thing? So go ahead, pause the video and figure out what the policy is that you're going to use for searching. Sorry. Pause the video, figure out what the policy is that you're going to use for searching together with your partner. Okay, so let's get started. Here's a policy. So first thing we're going to do is we're going to figure out the drawer for the number. So remember, a number comes in and we want to get the name. So how are we going to figure out the drawer? Well, we're going to look at the last digit of the number. So we'll look at the last digit of the number and we use that to look in a drawer. So we check if the drawer is empty. If the drawer is not empty, that means there's a note in it. Then we check the note and we see if the number on the note matches the number we have. If it does, that's great. That means we have the answer and the name is written on the note and we can go ahead and use that. If it doesn't match, then we go look up the name in the phone book. So if it doesn't match, or if the drawer is empty, then we go to the phone book, we look it up, we make a new note with the name and number, and we put it in the correct drawer. Okay, so first we're going to use the number to find the drawer, look and see if it's empty, or if it has a number in it, in which case we're all set. If it doesn't have the number, or if it's not empty, then we're going to go to the phone book, create a new note, and look for that. All right, so can you have other policies? Is this the only thing you can do? And the answer is absolutely. So right now we're going to start out looking in one drawer, but maybe you could look in two drawers each time. That'll take you 2 seconds each time you look because you have to look in two drawers, but you could certainly do that instead. But what I have here, we're just going to do this policy. Okay, here's a worksheet for you to work on here. You can see we've got a bunch of calls, the amount of time we spend in the drawer in the phone book, and the total time per call. And these are your drawers. So you can keep track of what's in each drawer as we go through it. You've got a phone book. It takes you 10 seconds to look up each number here, each number and name. Here are all the numbers. Here are all the names. So now I'm going to go ahead and I'm going to tell you who calls. And your job is to take that call, take your worksheet, and go through and do what you need to do in your policy to figure out how to handle each number. So the first number is this one here, 781-729-5555. So go through your policy, figure out how that works in your sheet there, what you do with the drawers, what you do with the phone book, and run through it. After you've done that one, then go through the rest of the numbers here. And you should end up with these people who called, but go through and work this out and figure out how much time it took. So go ahead, pause the video and do this together with your partner. All right, so let's see how did it work out. So the first number we had here was this one that ended in 5. So we're going to use 5 to figure out what drawer it is. We look at the drawer, it's empty, so we go to the phone book. And now the phone book's really slow, so it's going to take us 10 seconds. But we put a note in there with the number and the name. So our first time we spent 1 second looking in the drawer, 1 second putting something in the drawer, and 10 seconds looking up the phone. Oh, sorry, in the phone book. So we spent 12 minutes on that one. So this was actually worse. If we hadn't had this drawers here, we would have only spent 10. We spent 12 instead. All right, here's our next number. So again, we look at the last digit to figure out which drawer it goes into. We look at the drawer, there's nothing there. So we go to the phone book, we take a new note, we put that note in there, and it's going to take the same amount of time. 1 second to check if there was anything there, 1 second to put the new note in, and 10 seconds to get from the phone book. So again, 12 seconds. Not doing so well so far. All right, here comes another number. Well, this number ends in 3, so we go to the drawer, and hey, there is a note there. But now how do we know if this is the right note? Well, we check the rest of the number that matches. So we look at the other parts of the number and we say, hey, they do actually match. So that's great. Now we know this is the right one. So now we just spent 1 second to look in the drawer. No seconds in the phone. So now we just got the full name with only 1 second of time to look it up. That's encouraging. Okay, so we're 10 times faster than if we had to go straight to the phone book. Here comes our next number. Well, we go to drawer 5. We look up in drawer 5. How do we know if it's the right one? We check the rest of the number. So we say, hey, these two numbers do match. Great. So the same thing. We're going much faster again. So we're fast again. Now we get another number. So this number ends in a 3. Okay, we go to the 3 drawer. How do we know if they're right? We check the numbers. So do these two numbers match? No, they don't. Okay, so this isn't the right number we have in there. So it doesn't match. So now we have to go to the phone book. So we go to the phone book. We create a new note. We go ahead and put that new note in there. All right, so that took us 1 + 1. We had to look in the drawer and put a new note. And we had to go to the phone book. So again, it took us a long time. Okay, here comes our next number. It ends in a 3. So we go look in the 3 drawer. Great. So there is one there. How do we know if it's right? We check the rest of the number. Well, again, these don't match. Okay, well, they don't match. So it's not the right one. So we have to go and do the same thing. We have to go to the phone book, look up the number, and put in a new note. And so it goes ahead and takes us more time. So we looked up 6 items. We had to check the drawer 10 times. We checked the phone book 4 times. Took us 50 times to do that. So this is faster than if we hadn't had the phone book. If we just had the phone book, it would have been 60 total, but we were able to do it in 50 instead. So we saved a fair amount of time here. Okay, so now let's go ahead and analyze this. So what were the problems we had with this design and how could we fix it? So go ahead and pause the video and answer this question together with your partner. All right, so let's take a look. So the problem we had was that Margaret ended in a 3 and Michael ended with a 3. These two conflicted. They ended up in the same drawer because the way we figured out where the index for them was by looking at the last number. So they got in the way. And that meant we kicked one out, we put another one in, we kicked it out, and they went back and forth and they fought for that same entry. So how could we fix it? Well, we could use an associative design. If we could have numbers that end in 3 be put in multiple drawers, then we could have one drawer which had this number that ended in 3, or another drawer that had that number ended in 3. So if we had two sets that we could put them in, then we could keep them both. Or we could use another number for the index. So if we use the first number here instead of the last one, these two wouldn't conflict. But if you remember from our numbers we had before, all the other ones started in 7, so then a lot of them would have conflicted there. Okay, so go through and figure out how this is a cache. Answer the following questions for what we did in the phone book. All right, so let's walk through this one. So what do we have in our cache? Well, here's what we were putting in our cache. So our address is the phone number. That's the address of what we were looking up, and the data was the name. So that's what we store in the cache. Now what's the tag? Well, the tag was the phone number except for the last digit. Remember, this is what we used to check and see if the value we had in the drawer was correct. And the index was the last digit. So this was the last digit here. That's the index. That's what we used to know where to look in the cache. And the tag is what we used to look and see if we had the right thing in the cache. What was the cache line size? Well, it was one name per cache entry. Our valid bit, well, if there was a note. If the drawer was empty, then it was invalid. Our dirty bit, well, we didn't have any. We never wrote to the data. We never changed the name once somebody was in the cache, so we didn't have to keep track if it was dirty. What type of cache of this? Well, this is a direct mapped cache. Each number went to one and only one place, so we knew exactly where to look. And what was the replacement policy? Well, because it was direct map, there's only one place things can go, so we don't have any choices about what we replace, so we didn't have to worry about the replacement policy. Okay, let's go through and work out some cache diagrams. So here we're going to draw a diagram of the following caches. So we're going to start off with this one here, 64 line direct mapped right through 8-byte line. So I'm going to do this one for you so you can then do the rest yourself. So we're going to have a tag because we need to find stuff. And then we're going to have 2 words of data because remember, each of our words is 4 bytes and we have 8 bytes in a line. So we have 2 words in there. We're also going to have a valid bit. So the valid bit is going to tell us whether the data in here is correct or whether we can trust the data. And now it's a 64 line cache, so we're going to have 64 of these. Okay? So now it's your turn. Go ahead, pause the video and answer the next 2 together with your partner. Okay, let's take a look at this one, the 256 line one. So we're going to have a tag. It's a 16-byte line. That means we're going to have 4 data words in there. Now it's write back. So that means in addition to valid, we're also going to have to keep track if it's dirty because we could have data in here that we've written to that hasn't been back in the memory, in which case we may mark it as dirty. And it's 256 lines, so we're going to have 256 of these. Now we have 4096 line, 4-way set associative write back 64-byte line. Okay, so 64-bit lines, we're going to have a whole bunch of these data words in there. We're going to have our same valid and dirty bits, and then we're going to have a bunch of these. So here we have 4 ways. So for each set here, we have 4 different cache lines in it. Then it's 4096 line cache, so we're going to have 1024 of these sets, with each set having 4 ways in it for 4096 total lines in the cache. All right. What did our phone book look like if we take that sort of way of drawing out a cache? So go ahead and pause the video and answer the questions together with your partner. Okay, so let's take a look here. Well, we had a 10-line direct mapped 1 number per line. So we had a tag. Tag was the number minus the last digit, and we had the data, and the data was the name. And we had a valid bit. Well, we didn't really have a valid bit. The valid bit was just, is there a node in the cache? And we had 10 of them. So that's what our cache looked like. How do we search the phone book? Well, we used the last digit to choose the entry. So the last digit was our index, which one of these we access. And then we compare the rest of the digits to the number. So that was our tag. Okay, now let's talk about how we search caches. So we have a 64-line direct map right through 8-byte line cache. We drew the picture of it before. So go ahead and draw how you search this cache and how many comparators you need to do so. So go ahead, pause the video, and answer the question together with your partner. All right, so here's what our cache looks like. And now how do we search this? Well, we're going to use the index bits from the address to say where we go. Remember, in our example we had from our phone book, we used the last digit as our index bits to tell us where we go. So we go here. Then we need to do the comparison. So we're going to take the tag bits and we're going to compare, is the thing in that index location correct? And include the valid bit because we need to make sure it's valid. If they are, we have a hit. Okay, now that's good so far, but what's the right data? Well, we get out 2 words of data for this hit because we've got 2 words in each cache line. So how do we choose them? Well, we're going to need a mux. And the mux is going to be based on the word bit. So there's a bit which tells us which word it is, and then we output that. All right, so for this design, we only need 1 comparator. And that's because our index bits tell us the one place that our address could be, and we just have to compare the tag to see if that one place was correct and the data was actually there. Now go ahead and do this for the 256 line fully associative cache. All right, here's our 256 line fully associative cache. So how do we do this? Well, we've got our tag and we're going to compare all of the bits in the address. And why is that? Well, because it's fully associative. That means that any address can go anywhere in this cache. So we don't have any index bits to tell us where to look. We have to look everywhere since every address can have anything. Okay, well, we can go ahead and compare a tag. That tells us if this first line in the cache is correct and our valid bit and see if there's a hit, but that only tells us if the first line is correct. Then we have to do a mux because we got to select which of these 4 words we want, because remember there are 4 words here and we only want 1 when we upload an address. And you do the word bits for that. Then we're going to go and we have to make a comparator for every single entry here, because remember it's fully associative, so it could be in any one of these. We're going to have to compare all of the tags for every entry against our address. So we need 256 comparators. We got to search on every line since the data could be anywhere in there. Okay. How about this last one? So here's our cache. And how are we going to do this? Well, this is an index. It's not a fully associative cache. So our index bits are going to tell us which one of these sets it goes into. We're going to compare the first line in that set, the first way here, to the tag bits and see if it's a match and if it's a hit by the valid bit. And then we've got a whole bunch of these entries here, a whole bunch of words because it's 64 bytes. So we're going to have to compare each one of those and select it based on the word bits. Sorry, not compare, select it. So the index bits tell us which set to look at. The word bits tell us which of the words in the cache line we want. And then the tag tells us was that the right one. But these index bits just tell us it's in one of these 4 ways. So we did this to check if it's in the first way over here, but we're going to have to do the same thing to check if it's in the second way, the same thing to check if it's in the third way, and the same thing to check if it's in the fourth way. And remember, this is because in the associative cache here, we know that this address has to be in one of these 4, but we don't know which of those 4 it is. So we have to check all of them. So for this one here, we need 4 comparators to search each of the 4 ways for where the data could be. Okay. Now let's talk about how the bits are used for addressing. So which bits are the actual word bits, the index bits, and the tag bits for this? So the first one here is for the first cache we had, that 64-line direct map right through 8-byte line. So here's what the cache looked like. So go ahead and see if you can figure out which bits you use for which part of this together with your partner. Okay, so it's an 8-byte line. So that means we have 2 words of data in there. So we need 1 bit to tell us which word we're going to choose. It's 64 lines here. That means we need 6 bits to tell us which one of those lines we're going to choose. So this is how we're going to use our addresses. So the lowest 2 bits are going to tell us which byte it is in the word. Remember, MIPS is word aligned, so these will always be 0. Then the 3rd bit is going to tell us which one of these words it is. Then we have 6 bits of index. Those 6 bits are going to tell us which place it could be in here. And then the rest are the tag. So the rest of the bits are the ones we're going to use to see if this is correct. Now remember, this is very similar to what we had with the phone book example. In the phone book example, we only had 1 name in each slot, so we didn't need a word bit, but we had the least significant bits used to tell us where to look. And that's what we're doing here. All right, go ahead and do the same thing for the 2 other cache designs we had as well. So let's take a look at these. So here we've got a 16-byte line. So 16-byte has 4 words. So we need 2 bits for that. We've got 256 lines, but it's fully associative. That means it can go anywhere, so we don't actually use any bits for the index. Remember, fully associative, it can go anywhere we want. So then we just have all the bits for the tag except for the ones that we use to pick the word and the byte. And that means that our tags are going to be larger and we have to search all the tags because it could go anywhere. So let's take a look at the last one here. So here we've got a 64-byte line that has 16 words in it. So we need 4 word bits to choose between which word we're going to read out. We've got 4,096 lines, but they're divided into 4 ways. So that means there's only 1,024 sets. So we only have 1,024 of these we need to look at, so we need 10 bits there. So now we're going to have this set up. We've got 4 bits to choose which one of these words if we find our data. We've got 10 bits to figure out which one of these 1,024 sets we look at. And then we use the tag to look in each 4 of the ways here to see if it's the correct one. Okay, now let's take a look at the overhead we have for these caches. So go ahead and calculate the number of bits that we use for storing the data and the bits we use for storing the other things, such as the tag and the dirty and valid bits, to figure out how efficient our caches are. Okay, so let's calculate this first one. So here's how it's set up. This is what we have for how many tag bits we have. So our data, in this cache, we have 64 lines. Each line has 8 bytes per line. So that's 512 bytes, or 4,096 bits of data. So this is the data we're storing in our cache. The overhead for each of those lines, we have 23 bits of tag plus 1 valid bit. So that means we're storing 1,536 bits of tag and valid bits. So that's our overhead. So this means our cache is 73% data. So most of it's data, because we've got a lot of data there, but we have a lot of stuff being used to store the tags and the valid bits. So go ahead and calculate this for the other 2 designs as well. Okay, so here's what we're using for that. Here's how many tag bits we have for this one. So the data, we've got 256 lines. It's 16 bytes per line. So that's 32,000 bits of data. The overhead, well, we've still got 256 lines, and each line needs 28 bits of tag, plus 1 valid bit, plus 1 dirty bit, so 7,600 bits. So here we're 81% data. And we're so much more data because this has 16 bytes per line instead of only 8 bytes per line, and we have only 1 tag for all of that. So we've got fewer tags for the number of data bits we're storing. Let's take a look at the last one here. So for this one, we got 4,096 lines. It's 64 bytes per line. Okay, so that's whatever this works out to, 2 million bits. And our overhead for each of those 4,096 lines, we have only 16 bits of tag, plus 1 valid bit, plus 1 dirty bit, so 73,000 bits. So here we're 97% data. So this cache is doing way better. And the reason it's doing better is because we have these larger lines. When you have 64-byte lines, you have a lot more data for each of the tags you have to store, so they become much more efficient. Okay, let's take a look at calculating the average memory access time. So go ahead, read the problem, and see if you can answer it together with your partner. Okay, let's go through this. So we've got a processor with 2 levels of cache here, level 1 and level 2, and 65% of the time it finds the data here, and the rest of the time it finds it here. So the question is, how long does it take to access memory? Well, we can calculate this. 65% of the time it takes 1 cycle to access this cache, and the remainder, 35% of the time, it takes the 5 cycles to get up here. So 2.4 cycles on average. Now, if we change it so that we can make this cache work more effectively and get a higher hit rate here, we can reduce it to 1.6 cycles and we get 33% faster. So trying to make your L1 cache work more effectively is really important for performance. All right, here are 2 extra problems. So go ahead, pause the video and see if you can answer them together with your partner. Okay. So which of the following assumptions is not required for caches to be effective? We don't have to access data in regular patterns. As long as it's recently used data that's used again, we don't have too much data so it'll fit, and data nearby, so it's in the same cache line is used, caches will work great, but caches can do basically whatever pattern you want. So how did we use caches to solve the problem with all of these memory accesses per instruction? So remember, we had to access the instruction, and every third one was accessing data. So how did we solve that? Well, we have separate instruction and data caches. That allows us to do one read for the instruction and a read for the data at the same time so they don't slow us down. All right, so go ahead and do your individual part of your reflection questions. Pause the video and answer these on your own. And now when you've got an answer for that, go ahead, swap your questions and see if you can help your partner out.